All right, folks, let's talk about Chapter 2 a little bit. So Chapter 2 deals with the chemistry of life, so we'll talk about atoms somewhat. We'll talk about some water, which is hugely important. It has some really neat properties, and then we'll finish up talking about biological molecules. Now, I'm not going to go into a great amount of detail on any of these. The other videos will do that. But I just kind of want to hit the highlights here. Right? So obviously, if we look at the building blocks of matter, we're talking about atoms. Atom is the smallest component that you can break matter up into, and it still maintains the properties of whatever that matter is. So if you have gold, for instance, or aluminum, the aluminum atom is the smallest particle you can break that matter up into and still have aluminum properties. If you break it down past the atomic level, then you start getting properties of subatomic particles, which aren't the same as that matter would be itself. And so atoms are made up of the nucleus, which contains the protons and the neutrons, and then outside the nucleus you have the electrons in these outer shells. Your book talks some about mass number and atomic number. So the atomic number is the number that you would see. Let me go here right quick. So the atomic number would be the number that you would see in the periodic table. It also happens to be the number of protons that an atom has. So if this atom has one, let me go back. If this atom has one proton, I need to turn my writing on here if I can. If it'll let me. Let me turn my screen ink on. Here we go. Maybe this will work. So if an atom has, it's still not going to let me do it. If an atom has one, or atomic number of 1, it's got 1 proton. If it's got an atomic number of 2, it's got 2 protons. 3 protons, so on and so forth. But what you'll notice is that, so for this atom, it's got 2 protons, right? So it would be helium, right? If I go back to the atomic, so there's atomic number of 2. 2 protons, so it's helium. Typically, it would have, well, I shouldn't say typically. Usually, it depends on the atom, but it's not uncommon to see if it's got 2 protons, it's going to have 2 neutrons as well. Neutrons have no charge, but they contribute to the mass of the atom. So this one would have maybe a mass of 4, and so if we go back and look, you can't really see it very well, but that is a 4. Notice here with hydrogen, it does have a mass of 1 because you typically only find the proton in the center, in the nucleus. But so on and so forth. And so what you'll notice if you look at the atomic number, usually the mass numbers are going to be about twice what that is because the neutrons contribute to that mass. Electrons don't contribute to mass. They're super small. They mostly only contribute to the energy or the ability of the atom to make bonds and cause reactions to occur. That's really what the electrons are doing. And so if you notice, electrons are negatively charged. So if I pull an electron away from an atom, so let's say this electron goes missing, right? What that means is this atom as a whole is going to be more positive now, right? So notice in this atom I have 2 negatives and 2 positives. Those cancel each other out, so this atom is neutral. If I pull that negative away, though, this whole thing becomes more positive. If for whatever reason I add another neutron here, or electron here, then this whole atom becomes more negative, right? And that's how we cause chemical reactions to occur. You can look over the periodic table. There's all sorts of things you can deduce from the periodic table. If this were a chemistry class, we could probably spend multiple lectures just studying this, but that's not what this is, and so I won't spend a whole lot of time on that. Right? So that's it. Protons, neutrons, electrons, periodic table. Talk a little bit about carbon dating. If we look at chemical bonds, there's a couple ways to form chemical bonds. If I go back to this quick little little PowerPoint. This one is showing you ways to do ionic bonds. And so one of the things we know is that atoms want to tend towards what's called the Octet Rule. And so if I look at this chlorine atom, for instance, and I count the number of electrons in this outer ring, 1, 2, 3, 4, 5, 6, 7. Typically, for any ring outside of this first one, the atom wants to have 8 electrons. That's the octet rule. And so if it doesn't have 8 electrons, it's going to try to figure out a way to get them. And so notice, again, 7 electrons here. So this chlorine atom wants 1 more electron. And then if I look at this sodium has 1 electron in its outer shell. And so if it could just get rid of that one, then it would have 1, 2, 3, 4, 5, 6, 7, 8 in the outer shell. And so what this sodium would like to do is just give this electron away, and what this chlorine would like to do would be to attract 1 electron. And so that's exactly what ionic bonds do. So chlorine would pull this electron in. So notice, remember what I said, if I add an electron, this whole atom becomes more negatively charged. Right, let me see if I can, I'd love to be able to write on these. Nope, that's not what I wanted to do. I'll do this. Right, so this whole atom becomes negative. We're still not going to do it. This whole atom becomes negatively charged, right, because I take this negative electron and add it to that outer shell. Although sodium, because it gives this electron away, it becomes positive, right? So if you think about a positive charge here and a negative charge over there, one thing we know about charges is opposites attract. And so, because I created a positive charge here and a negative charge there, that sodium and that chlorine want to stick together. And by sticking together, that gives you table salt. That's what table salt is. It's simply sodium chloride. And what we know about sodium chloride is it's relatively harmful. In fact, you need it. You need salt in your diet. That's what contributes to your electrolytes. Now, you don't want too much, but you certainly don't want too little either, because that can cause you to have problems as well. And so those would be ionic bonds. Then we can look at covalent bonding. So what happens with covalent bonding is you end up sharing electrons. And let me go back to your book here. Here, covalent bonds. So in covalent bonds, instead of giving an electron, you share it. And so what happens in the case of maybe something like oxygen and hydrogens, well, oxygen would have 6 electrons in its outer shell, so it would need 2 more to get to 8. Hydrogens only have 1 electron in its outer shell, so it needs 1 more to get to 2. And so what happens is, instead of hydrogen giving an electron or oxygen giving an electron, they just share them. So the electrons would spend some time around hydrogen and some time around oxygen, and then more time around hydrogen, more time around oxygen. And they would just keep doing this, back and forth and kind of sharing that electron instead of just completely giving it away. And that's what's creating these covalent bonds. Now, whether it's polar or nonpolar, just really points at how much sharing is there. So in a polar covalent bond, what that means is the electron is spending more time around one atom than it is the others. And in the case of water, the electrons spend more time around oxygen than they do hydrogen. One way to think about this is think about oxygen as being a bigger molecule, and so it just takes longer for the electron to get around the oxygen and then come back around the hydrogen. Technically not what's happening, but it's a good way to kind of remember it. So if the electron spends more time around oxygen, that means that part of that molecule becomes slightly negative, and if it spends less time around hydrogen, the electron, then that part of that molecule becomes more positive. And so because we generate these positive and negative regions in the water, we call it a polar covalent bond. Think about what polar things are. So the Earth is polar, magnets are polar, batteries are polar. Something that's polar means one end's different than the other, right? So the Earth has a north and a south pole. Magnets have north and south poles. Batteries have positive and negative terminals. So the same is true for polar covalent bonds, right? They have a positive and a negative region. In nonpolar covalent bonds, so a simple one to think of is just oxygen, these are the same atom, and so the electrons aren't going to spend any more time around one atom than they are the other. It's going to equally share those electrons, and so those are going to be nonpolar covalent bonds. Right? And typically, anytime you see something that's kind of symmetrical, right? So here with these carbon-hydrogen bonds, so hydrogen's evenly dispersed around the carbon, or anytime you're bonding two of the same atom together, those are probably going to be nonpolar covalent bonds. Something like this, water, on the other hand, would be polar covalent. Right? And so then we get into something called hydrogen bonds. If I take a polar covalent bond and I have these positive and negative regions, remember, positives and negatives want to stick together, and so what happens is this negative region of this water molecule wants to stick to the positive region of another one. And so if I just scroll down here, we can see that, right? So there's the negative oxygen, the positive hydrogen, they want to stick together, and that creates what we call a hydrogen bond. You have seen the consequence of hydrogen bonds, whether you realize it or not. If I look at something, I think there's something in the PowerPoint slide. Let's see. Here they're showing you that this needle is floating on top of the water. Or if you've ever seen those little water striders that can skip across the top of the water. Or maybe you just pour pepper on top of water and just kind of see it float on the top. The reason it's doing that is because of the surface tension that's created in water. And the surface tension is really just the attraction of water molecules to each other. Right? So the water wants to stick together. And that force is great enough that things that sit on top of it, if they're not too heavy, they don't break those bonds, and so it can just rest right on top of it. We can kind of break those bonds, though, with things called surfactants, which are soaps, and that lets water more evenly distribute. You'll see surfactants oftentimes in maybe an herbicide or a pesticide. When you spray things like that on plants oftentimes have a waxy covering on their leaves, and so the water wants to hit, beat up, and roll off because of these hydrogen bonds or this surface tension. So if I can put something in the water that relieves those hydrogen bonds, removes that surface tension, the water won't hit and roll off. It'll hit and spread out. And so knowing how to take care of those can be beneficial. Right? Let's go back to the text. And then some more properties of water. Obviously, it's polar. This is also why oil and water don't mix very well. So polar and non-polar things typically won't mix. If you put oil in water, the oil beads up and won't mix. It won't dissolve in the water because oil is non-polar, whereas water is polar. Maybe so. Let's say I change the oil in my truck. And then when I'm done, I have some grease on my hands and I don't get it all washed off, right? And then I go to lunch and I eat some French fries and then I look at my fingers and I notice some of the oil came off. Well, where did it go? The oil from the French fries, which is non-polar, mixed with the non-polar oil that was on my hands, they dissolved each other, right? And so in that sense, polar things tend to dissolve other polar things and non-polar things tend to dissolve other non-polar things. Also, things like water, which is polar, tends to break ionic bonds or dissolve them relatively easily too, and that's what this is showing you here. If I have something like sodium chloride, the reason it dissolves in water is because of that polar nature of water. Right? So that's what makes water a good solvent. The other good thing about water is how temperature stable it is. Water takes a whole lot of heat to increase its temperature. Inversely, you have to remove a lot of heat from water to decrease its temperature. That's why water is so good for us, and because we're mostly water, our temperature doesn't fluctuate too much. If you put water on the stove, for instance, and heat it up to boiling, turn the stove off, come back an hour later, and it's still pretty dang hot. That's because it takes so much energy to remove that heat back out of water. It's also why water is good at cooling us off. When you sweat and that water leaves and evaporates, it took so much heat to evaporate that water. It pulled that heat away from you, causes you to cool down. The other thing is true as well. So when water freezes, right, so the act of freezing water, you have to pull heat out of the water in order to cool it off. You may have wondered why, so maybe orange groves. If there's a freeze coming and there's oranges on the trees, they'll spray them with water. Why? Well, because as the water is actively freezing, in that little microclimate, it's not going to drop below the freezing point, right? Once water stops actively freezing, though, then the temperature can drop. And so that's another kind of good to know, right? If you have maybe a vineyard or an orchard and you want to prevent crop loss from freezing, right? So it helps stabilize temperatures, right? Good solvent, it's cohesive, right? You may have also noticed if you take a small, let's see if I have one. If I take a small cylinder, right, like this graduated cylinder, if I was to fill it up with water, what you would notice is that there would be kind of a dip in the middle, right? It would look like the water is forming a U. Why? Well, because the water wants to stick to the side of the graduated cylinder. It wants to climb up it because the cohesive properties, or the adhesive properties, my fault. Adhesive properties, so for something to be adhesive, it sticks to something else. If it's cohesive, it sticks to itself. Water is both adhesive and cohesive. So because the adhesive properties of water, it wants to stick to the sides, and because the cohesive properties, it wants to stick to itself. And so water is actually wanting to kind of try to climb the glass. And the smaller the diameter you can make this cylinder, the more pronounced you'll see that U. You don't see it great in this one because this one's kind of large, but you can still see it. It creates that meniscus. You may have heard of that. And why you have to kind of be careful of how you read graduated cylinders, right? So cohesion and adhesion. Water also contributes to pH. So in pure water, you have just as many hydrogens as you do hydroxyls, so HOH. If those two things are equal, so H's and OH's, let's see if I got this on this PowerPoint, right? So if the hydrogen, right, think about water, H2O, HOH, right? So if I have just as many H's as I do OH's, right, 1 for 1, then that would be a pH 7. Purely distilled water. If I move one way or the other, so let's say I get more hydrogens than I have OHs, so more H's than OHs, then things become more acidic. If I get more OHs than H's, right, then things become more basic, and we call that the pH scale. Things that are acidic are things that have more hydrogen ions. Things that are basic have less hydrogen ions. Again, you could get into the chemistry of that, and it can get pretty complex. But for us, in here, that's enough, right? And so you can think about things that are more basic and things that are more acidic, right? And this can fluctuate a little bit, right? So, for instance, in your stomach, it can fluctuate from maybe a 1 to a 3. But things that are typically cleaners, like ammonias or bleaches, those are usually pretty high pHs. The other thing to know about the pH scale is it's logarithmic. So what that means is instead of going up by 1 each time, so distilled water up to seawater, so from a 7 to an 8, that's a factor of 10 pH, right? So 9 is 10 times more basic than 8. 8 is 10 times more basic than 7. 9 is 100 times more basic than 7. So it goes up by a factor of 10 each time, right? 1 is 10 times more acidic than 2, but 1 is 100 times more acidic than 3, right? Hope that makes sense. But here you can, in this paragraph, you can see them talk about the H and the OH, which I mentioned. Probably the most important thing in this chapter are the differences between the biological molecules. or the organic molecules. Organic, the term organic has kind of been stolen from science. Really, organic means things that have carbon-hydrogen bonds, and in science it doesn't really have anything to do with whether it's been sprayed with a pesticide or not. So organic molecules are molecules of living organisms, contain carbon-hydrogen bonds. So one of the major macromolecules or biological molecules are carbohydrates. Carbohydrates are things like sugars and starches. The simplest is a monosaccharide, mono for one, saccharide for sugar. These would be things like glucoses or fructoses. Glucose is hugely important to us because our mitochondria break them down and release a lot of ATP. Fructoses are fruit sugars. And so a common thing that you see maybe in the dieting world is they'll tell you that sugar is toxic and that you should avoid it. What you should avoid is too much, right? So you don't want too much of anything. Sugar itself is not toxic. In fact, it's beneficial. You need it in order to release a lot of energy. That's the reason you like it, right? It's no coincidence that you like fatty foods, salty foods, sweet foods. Like those are all things, macromolecules that your body needs. That's the reason that you like them. The problem is when you consume too much of any of those. Too much fat, too much sugar, right? Too much protein can be a problem, right? So too much, honestly, too much water. You can consume too much water, and people have. It can cause your brain to swell. Now, you would probably urinate before it got to that point, but it has happened before. Water toxicity is a thing. Carbohydrates. So carbs can be monosaccharides, they can be disaccharides. So if I take two glucose molecules and stick them together, that goes from a monosaccharide to a disaccharide. One of the most common disaccharides is sucrose, which is table sugar, which most people have in their house. And then we can get up to polysaccharides, which are things like starches, glycogen, and cellulose. Starch is how plants store carbohydrates, potatoes. High in starch because they store all that sugar as starches. Glycogen is how animals store carbohydrates. So you store a lot of glycogen in your liver, for instance. When you go to sleep at night, your blood sugar levels start to drop. You go to the glycogen stores in your liver to release that glycogen, break it down, and return some sugar back to your bloodstream. Cellulose, that tends to be fiber in plants. If you look at a tree, most of a tree is cellulose. It's not very digestible. That's why cellulose is good for the gastrointestinal system. You hear a lot of talk about using fiber in your diet or needing fiber in your diet, and that's why, right? Very important. So that was carbohydrates. That's one of the biological molecules. Lipids is the other. So lipids are fats, oils, and waxes. One of the major lipids would be triglycerides. They can be either saturated or unsaturated. The easiest way, if you're looking at one, it's saturated if it looks relatively straight. Right? It's unsaturated if it has this double bond kink in it. And that's as kind of far as I'll take that. So if I show you a structure that looks like this and say, is it saturated or unsaturated? Well, that one is saturated. Right? What that really means is it's saturated with hydrogen bonds. It's got as many hydrogens around each of those carbons as possible. In an unsaturated, it ends up with a double bond, and so you don't have as many hydrogens around. And you could count these up. Right? So there's 3, 4, 5, 6, 7, 8, 9, 10, 11. You could count those and then compare it to this one. And what you would find out is this one has more hydrogens than that one. That one is saturated. That one is unsaturated. Another way that you see the difference between saturated and unsaturated fats is saturated fats. Those tend to be solid at room temperature. So things like butter, things like bacon grease. Right? Once it's in the pan, it gets back to room temperature, it kind of sets up. Unsaturated, things like olive oil, right? They're liquid at room temperature, right? And it all has to do with that little double bond there. Right? And here it's showing you the difference between those two. I don't care that you know the difference between cis and trans fats. That's an organic chemistry thing. I want you to know saturated and unsaturated. Phospholipids are important. So phospholipids aren't triglycerides, they're diglycerides. They only have two kind of fatty acid chains with them. I think, let's see. They don't have a good one. Let me see if I can show you a phospholipid right quick. So here we go. Here's all sorts of phospholipids, right? So notice that they don't have three tails. They've got two, where a triglyceride would have three tails. The important thing about phospholipids is that it creates these bilayers, right? So if I take one phospholipid and stack it on another and then continue to do that, I create this membrane, and that's what cell membranes are made up of. Right? They're made up of this phospholipid bilayer, right? So extremely important molecules are phospholipids. Also, steroids are lipid molecules. Steroids can range from cholesterols through. I mean, maybe you've taken prednisone as a steroid to reduce inflammation. Steroids are pretty diverse. Any waxes are also lipids, right? So a pretty diverse group of molecules there. One thing about lipids is that they're super energy, like they contain a lot of energy in them. That's why it's so hard to break down fat in us, because you have to do so much work in order to get rid of it. You have to be in a calorie deficit and do a lot of work to get rid of fat because it's so high in energy. 1 gram of fat compared to 1 gram of sugar, you'd have a whole lot more energy in the fat than the sugar. That's why we store them the way we do, right? Because it's convenient. Then we've got proteins. Proteins can do a lot of things too. They can be enzymes, they can be hormones. They're made up of amino acids. We are essentially just sacks of protein walking around. It all comes from DNA. So DNA makes messenger RNA, which is the code for protein. But a lot of your hormones, like insulin, for example, right, are proteins. That's also the reason that you have to inject insulin. Science is working on a pill form, but because it's a protein, once it hits the acidity of your stomach, and there's enzymes there that would break it down. It's right now just easier to inject something like insulin to cause it to work than it would be to take it orally. Proteins can have a bunch of different structures, so they can be primary. So if you look at this kind of string of pearls type deal, if you fold that string a little bit and get some complexity, then that's the secondary structure. If you fold it even more, you get this tertiary structure. And then if you put several of those tertiary structures together, you get this quaternary structure. Proteins typically are really complex, really large molecules that are at this level, this quaternary structure. Things like the heme protein and hemoglobin, right? It's really large as far as proteins or as far as molecules go, and it has that quaternary structure to it. And then nucleic acids. Nucleic acids carry a lot of information. It's the DNA and the RNA in your cells, and it creates either this double helix in DNA form or in RNA form. There's not two strands, there's just the one, right? So again, the major biological molecules are carbohydrates, proteins, lipids, nucleic acids. That's the 4 big ones, and then you can kind of break them down from there. So maybe do like a little chart, put the 4 across the top, and then list out what they are independently. And then you've got your review, so maybe go through these chapter summary questions and some of the review questions and see if you can come up with any questions for me. and shoot them to me, and I will be happy to answer them.